which is subset of deep layer. So you need to understand neural networks, different types of neural networks, deep neural networks, and part of reinforcement learning to understand generative AI. Understand straight away if you know that's kind of black box. Okay, you want to do research and you want to do something, you want to excel as a developer, a software engineer, you need to understand core concepts. So for that, you need to understand first at least neural networks, deep basics at least. Then you can excel in generative AI. Okay. Okay. So CNN, RNN, you might have studied your syllabus. I don't want to touch those things right now. So my complete objective is why, like RNNs are there. Why we need again transformers? So someone of you asked, raised very good question. Like partially, no, I answered that question as well in the coming slides. So earlier we have CNN for image-related features to extract and for classification problems. Now we have RNN, of course. RNN, an extension to that. RNN fail in a lot of cases. I'll show you the examples also this in the next slide. Yeah, LSTM, all those things will fail even if you use attention with that. Okay. So what is this attention mechanism? Suppose there is a movie, some interested movie. Let us consider Prabhas movie. Okay. So first day you sit in the last bench, VIP gallery, and you are watching some song. Generally, what do you watch in that? There is a I can say song is going on, heroine dance or something is going on. So your concentration is mostly on heroine, but not on the background dancers and background maybe at Himalayas or some New York City center somewhere, right? Most of the cases, our complete concentration. So that means you are paying attention at particular location in that image or video, right? So that is our human psychology. Mostly we concentrate on something which is interested, which we are interested, right? That can be anything. It can be anything. So that's where actually, but how to teach that to a machine? Machine also need to think like you, right? Then only it can act like you. Then only it can answer like a radiologist or an expert. If you ask a question about radiologist, what is the issue, so and so, it has to analyze the image and has to tell. So this is the issue and all. So machine also need to think about the same fashion, right? So that's what attention is. In the earlier models, RNN, LSTM, most of the cases, this attention mechanism is not there. And even they introduced in maybe before 2017, like 15, 16, but most of the cases in real-time problems, it failed. Right? So the examples also. Then I will see more on this. 2017 paper, I request all of you go through this paper. So of course, high-level architecture I will explain. So why transformers? So when you have huge amount of data with self-attention, it works almost like an intelligent machine where it can respond and it try to mimic a kind of with the language, mimic like a language expert and so on. Okay. So, but what we need, massive amount of data is required. So for training, why we need data? To train. So machine can learn from the data, right? Right? We need huge amount of data. That is supervisor data, supervisor learning, data, unlimited data, combination that. But we need huge amount of data. Okay. So see this one, generative pre-trained transformer. So I am talking about data. If you see GPT-4, GPT-2, GPT, the different versions I have given here, but number of parameters are different. What are those parameters? In deep neural network or any neural network, you have a number of parameters from layer to layer, right? That are passing from layer to layer. So these are learnable parameters. It learns something from the data. Then after learning, when you give a new task, it automatically gives the solution. That can be a classification, segmentation, or name and recognition, whatever the application, right? So what I'm trying to say is each version of GPT, if you see GPT-2, maybe millions, next GPT-3, billions, then GPT-4, 1.8 trillion, GPT-5, 1.8 trillion parameters. Data is very, very important. and if you can reduce number of parameters, still it can learn the model, then it is very good. Okay, so that also we see. So this paper 2017, it has 12 layers, decoder and 8 encoder models. Sorry, total six encoder layers, 6 decoder layers. We see complete architecture. So 12 layers, each layer performs the same task, which is a repetition. Okay, and there is a concept called self-attention followed by parallelization, where RNN doesn't have parallelization. So it's a sequential thing. You have to give one word by word it process and it is the next word or whatever it is. But here parallelization is there, highly parallelizable. So how it is highly parallelizable, we'll see. Okay. Yeah, see this one. A simple example. RNN, we are just giving this is x1 is one word and so on, n number of words. So this one is transformer. If you observe x1, x2, x1 is connected with two words, x2, x3, x4. Why we need to parallelly I'm giving all the words, 10 words are there, 100 words are there, 1000 words are there, every time I'm giving all the sentences, entire text. Okay, that can be a story also, but it actually works parallelly. And if you see x1, so I love India, for example, if you get a statement, I is cross-checked with love, love is cross-checked with other word, each and every word in the sentence, how these are relevant. Why should we check the relevance? So I can just translate the given I with some encoding in kind of numerical representation followed by for each and every word there is a numerical representation. Then I can just obtain it and finally I get some output. That's not my objective. So if you get that objective, it is static. So where RNN and LSTM does the same job. But here self-attention mechanism, it learns from the data. At the same time, how important each word. Your language is so easy. I'll show some examples why we need attention mechanism. See this one. I hope everybody can see last. I hope you can see sentence. Can you read this sentence quickly? The chicken did not cross the road because it was too tight. What is this? It refers to chicken. Sure? Okay. So how do you say it refers to chicken only? So grammatical rules and sentence and formation and relationship between words also. As a human, you learn English, right? But how do you teach the same thing to a machine? So in stat like RN and LSM, if you go, you have a equal kind of vector representation. A numerical vector representation is there. That is fixed for each and every static. But it doesn't work here. If you go with that, it can be like referred to any other word, can be because road, anything. But say immediately it refers to only thing, right? That machine need to understand. That's what the self-attention mechanism is. Okay, I'll show you that. How it learns. Okay, so that's what the contextual embedding is. So this self-attention. So see the second sentence. The chicken didn't cross the road because it was too wide. Now, in the second case, what is it refers to? Road. Now it is just I just added one word. How it simply changed the context. So till this hit, both are same, right? Isn't it? Both are same. Where's the difference? Was two word. Last two words or three words are different. Because of that, what happened? Meaning is completely changed. It refers to something else, isn't it? Then how can we teach the same thing to a machine? So with static, say models like LSTM and RNN models, you could not find what is that difference. So there is a tight relationship between words. I'm trying to say in language. So you need to understand what is the context and what is the relationship between each and every word. Understand? So that is the speciality of transformers. Okay, we see how this is another sentence. Here it's not about the word but complete. She saw the man with the telescope. So we have interpretations here. First one, say. First interpretation is correct only, right? Say yes or no? Yes, good. Second interpretation, she used a telescope to see the map. Second one is also correct, right? So which context is correct now? Both correct, but only one is correct. I'm saying. So now it is not about one sentence. Now I have a big paragraph. If I read the big paragraph completely, then only machine will understand what is the context, isn't it? If you read the complete story, then only you will understand what is the interpretation of this sentence. So that is not there in RNN and LSTM. What you learn in your part of syllabus, deep learning syllabus. Okay. Now how this context and word relationships, how the machine will understand. So that is the beauty of transformer. We're going to see. So I hope you studied data structures, hash tables, everybody as a basic course, right? What is this? I have a query and I have a hash function, some modular division, some some hash technique I use here to find out the key. Using the key, I find out what is the actual address. So I'm just searching in because of one time complexity using I have a query. So this query is where that hash table using some hash function. Right? This is the hash. So query. So using hash function get a key. What is the value at that place at that address? I can see. In second, I'm trying to see that I have a this query is, for example, I have a big sentence. As assume as it. Now this it word, now this it word is relevant to all the other words in that sentence. I'm finding. Is it really more important or relevant to the word it with the previous word chicken or road, whatever it is, and so on. I'll find out the relevance with each and every word. Understand? Then, so I give more important words. For example, road you are saying, I am saying other one chicken. So where I'll retrieve like highest values. For all the other values, this dull V0, V1 values, which means smaller relevance with that word. Understand? One word with all the other words, I'm just finding how it is relevant to all the other words. Based on that, if it's more relevant, I get a bigger value. If it is less relevant, I get small value. Understand? Yeah. So this is the architecture of transformer. So input embeddings, positional encoding. Then we have a lot of layers. In deep learning, you might have studied what is add and normalization, and for feed-forward network and add and normalization. As I told you, it's again a deep learning model. We have n number of such layers in the encoder part, and decoder part also you have n number of such layers. Similar architecture. Of course, I'll quickly explain this. This is your input. Just now we have given one sentence. This is your input. Okay. So encoder and decoder, two architectures we have. So we just get up this notation of RNNs. Okay, we have a new things like KI, VI, QZ, and VZ. Right? Yeah. So we have a positional encoding. When I say parallel, I have n number of words. Even I can take 100 sentences at a time. So, but when you say parallel, you want to process. Obviously, what is the relevance I'm going to find? Right? So find out the relevance, identify uniquely each and every word, assign with some. Yeah. Now the language again. Translation task. If I say I'm giving some sentence, I'm just translating this to. Can be I'm predicting the next word, or I can translate that to one language to another. For example, English to Telugu, English to Hindi, and so on. Okay, so you can use transform for different tasks, but mostly they designed it for language translation. Okay, input tokens, which what we are giving, and this is when you give so long, then input as so long. What is the next word? What is the probability for the next word, and so on. This is a layer by architecture actually, right? This is how it actually translates. Now I am saying self-attention mechanism, which actually finds the relevance of each one and give more attention to the word chicken. And if you see the road, which has more relevance, like with the word it. That's why it is given. Thick indicates the higher values, as I told you. Okay. Next. Yeah. So this is how actually we calculate. See, these are words. When you are calculating xi, you are going to see all the relevant words, like previous words, how this xi is relevant to this. So how can you calculate that? We are just calculating these whatever the vectors that is generated. We are multiplying that, and then we are applying the softmax function. So which is again probability between 0 and 1, it generates some value, and then alpha ij. So you know the learnable parameters here. It need to learn whatever this language translation, whatever you take, it has to learn from the data. So we have some parameters, that is alpha ij xj. So xj is your input from j less than or equal to 1. If you start from 1 to j equal to 1 to I, all the words till we are going to calculate. I can say to generate the next word. AI is next word, right? Yeah, this one. When you are calculating A5, we are just multiplying A1 to this is AJ, this is I. So all the words you have to attention values and the parameters, everything we are multiplying here, right? J times xj is your actual parameter. It learns from the data. Different examples you are giving, 1000 examples you are giving, from the 1000 examples it is learning. So when you give new sentence, automatically it can translate based on those parameters, right? So these are the query key value. What is the query? Whatever the word you are giving. What is the key? Yes. So how this particular query is relevant to each and every word. Then based on the relevance, it generates a value. I hope it's clear. What is query Q value, right? Last, whatever the it that is given, how it is relevant to all the words. It is your query. Then remaining all words, that is key. All those are keys actually. So you are considering it with each and every word previously in that sequence. Then based on the relevance, if it is a less relevant, you will get small value. If it is more relevant, you will get a higher value. That is your value. Okay? Yeah. So fine. Now some parameters are required if you take any deep learning model. So our machine learning model. So some of the parameters we are using W, Q, WK, and WB. These are the parameters. So we are actually training with a lot of examples. So these are the parameters which are learnable from the input data. So finally, each and every word is calculated. Such a complex model this one is, but at least you need to understand the basic thing. So input is given, then we are calculating the query key value, and we are multiplying with some constant value dk, which is the model length. So to actually optimize, like instead of growing these values beyond some value, like limit, we are just dividing the square root of dk, and then with weights, which is we are applying the softmax function followed by each value vector we are generating, and then sum of these values. Finally, we are finding one value output. That is, if I am saying I love, what is the next word? Based on these two, what is the highest probability? A3 is India, for example. So if you give more data related to India, obviously it will predict next word as India, and so on. This is how next word is predicted using transformer. Okay. Now we are saying parallelizable. So that also we will see parallelizable. Calculated, that is actually one head. Now we are going to see multiple heads. If you see whatever we are seeing, that is for one head. So when I say parallelizable, the similar thing happen in a n number of heads. Here they propose 8 heads. So parallelly, one sentence, another sentence, n number of sentences are there. Each and every word parallelly, 8 heads are working and finds that self-attention values. How each and every word is relevant. Okay. So I have 8 heads in this multi-head attention. Finally, input is given. Encoder part, we have 6 encoder layers, again 6 decoder layers. So we are training this. Again, as usually, there is a back propagation, forward propagation, back propagation is there. So it predicts the next word, which is given as the positional encoding to this input at the decoder end. Finally, it is a kind of regressive decoding, auto-regressive decoding, and it predicts the next word. Okay. So this is all about multi-head detection and the architecture. This high-level architecture. Fine. Now, based on this transformer, GPT, BET model, and Robert A, and so on. So, if you see this one, OpenAI come up with GPT, generative pre-trained transformer, BET. So this is actually transformer is for language related tasks. Now, I have a classification problem, segmentation problem, name entity recognition, so on and so on. Lot of problems are there. I can't solve every problem with transformer. So that's why Google come up with the BET model, okay, which is a pre-trained transformer. Similar thing, I'll show you the simple architecture. Robert A, so which is again by Facebook, transformer based language model. Okay, specific applications they designed, they changed the architecture and they come up with new idea. Okay, so this is BET, which was introduced in 2008. Okay, see this is encoder only model. So if you see transformer encoder, n number of encoders are there. I don't have decoder. There's no decoder. Why? Because my problem is different. Whatever the encoder, like 6 encoder layers are there, I use 12 encoder layers only. What is my task now? I can use just it as a translation or for classification also input sequence is given something like this. Sorry, you have 12 layers here. Transformer encoder 1, 2, and so on. 12 layers are here, which we are calling base model. Okay, so this is used for classification, name and recognition, and so on. The same functionality, whatever we discuss in the encoder part of the transformer, the same thing. Okay, but here one token is there, which we call it as CLS token, which is the representation of all the layers with one token node. Here we call it as CLS or classification. Complete representation of all the layers, which is given with this one, which is used as end of the layer. We have a softmax layer. Softmax layer, again there is a probability game. It finds. So if there is a classification task, it is a dog, cat, whatever it is. It's a multi-class classification problem. I have 10 classes. So out of 10 classes, what is that class? Okay. Yeah. No. Deep learning. When I say deep learning, I have 20 layers. ResNet consists of 50 layers, right? So if you observe, what is this? There is a residual connection. What is the residual connection? ResNet. How many of you heard about ResNet? Which solves the vanishing gradient problem. So where we are preserving the input features and which are connected to the directly to the next layer, right? So I forgot to tell that. Because of time constraint, just high level architecture I thought to explain. There is a residual connection which preserve input features. So layer by layer, when you are manipulating with some random weights, so you lose the actual content, actual input features. So for that ResNet, they actually it is a combination of a lot of work that has been done till this date. Residual connection ResNet is the best one in image classification. One of the best I can say, ResNet 50 or ResNet 30. So that's how it solves that vanishing gradient problem. So finally, it generates this attention mechanism values. So we'll get best classification result. Okay, CLS is the. Now, what is your task? Yes, listen. So this is class now. This is for students. Now our actual problems, open problems, we're going to discuss now. So can you train such a huge amount of data with the limited machine Colab or Powell? Or in your inbuilt GPU? No, we can't train millions of. Just see this one. The BET objective. So they train with Wikipedia. Can you train your model with the entire Wikipedia model? No, right? You can't. You don't have that much, computational, power, right? So obviously, BET is providing you a pre-trained model. you open a website, Hugging Face. Okay. So what version you want, base model you want, bet A, Robert, Albert. These are all names only. I am not giving my own names. These are all models that are available in Hugging Face. Just open this. This is a bet model, which is already trained with Wikipedia. On top of that, if you have small limited data, you can just fine tune your data with the available bet pre-trained model from Hugging Face. Just fine tune it so that you can use for your specific task. Okay. So one of your mini project, like as deep learning part of your course, you can take a small project, mini project, and you can do. You can fine tune specific keyword. Say that can be medical related, banking related, anything. Okay, sports related, you can take. Okay, small data set to identify, users better, fine tune. Then maybe it can be a classification problem, summarization, whatever it is. Okay. Similarly, GPT-1, if you observe, so what's the first area? Decoder. So previous bet model is encoder only model. What about this? Decoder only model, right? So that is designed for a specific purpose, and this one they have changed for other application. They use only the decoder part. 12 layers of decoder of transformer, and they are finding that they're using this for something else, some other application, right? So see this GPT 1.5 and 175 billion. These are number of parameters. You can't train this, but what you can do, I've shown you one task. I'll show you some applications also where you can explore. So GPT, again, see how much training. How much training data is there? I'll show you that slide. I think I missed that. GPT is trained on, trained on corpus of 10,000 books and common crawl a large data set of web pages. So can you train? No. In-house you can't train. What you can do? Pre-trained models are available. Okay, take that. You can use it for your specific task. Okay, yeah. Okay, some of the applications I can show you quickly. Machine translation. So there is Google Translate is there. You can explore. You can work out. So maybe if you want to pre-trained model is available, you can try for local languages and all if it's not available. Next, text summarization, bet sum. Just now I have seen the bet high level architecture. So bet sum is which is available in Hugging Face. You can explore that, which is for text summarization. So I don't want to read a research paper. Okay, so I just upload entire 5 pages, 6 pages, or 10 pages of the research paper. I want just summarization. And you can also customize this. You can come up with pre-trained model is available. You can also just try to understand that maybe in a month or 2 months, then try to apply that for fine tune that for a different application. These are all available in Hugging Face. Text generation, OpenAI's GPT-3 anyway. You might have used GPT-4 also. GPT-5 also released right 2-3 months back recently. And for sentiment analysis, you have Robert A. Just now I told you Robert A. For sentiment classification. These are all applications. Question answering, name entity recognition. We have specific question answering anyway bet is designed for that. And then spaces, transformer models, which is for name entity recognition. So you can select any one of these applications if someone is interested in this domain. Image captioning, image GPT is there. OpenAI Codex for code generation. Okay, so it can generate code. Model itself can generate code, right? Yeah. Next. So face recognition synthesis with transformer transducer, which is extension for transformer. Then drug discovery, just imagine molecule transformer. Okay, so where you can again extend the work, like you take the basic drug discovery molecular transformer. Maybe for few molecules it may not work. You identify what are the like inputs that are considered for pre-training, part of pre-training. So for some drugs it is not available. Then you can find, you can change, even you can change the complete architecture also with the molecule transfer. You can take this as your capstone project and try. Understand all these applications based on transformer only, right? So next thing, how you can use vision transformer. Say concept is same, okay, but it is just combination of like transformer, but we are using it for image applications, right? So see this one. This is our image. This is divided into different patches like this. Each patch is a token, like how we are giving a big sentence. Same thing is given, divided into patches, and give this each patch as a token to your vision transform. Understand? So now it has earlier it try to consider each and every word relevance, but now each and every patch, how this patch is relevant to, and because we are just converting this into image into a token, kind of a grid. This dimension is they consider 16 plus 16. If you want, you can take, I think you might have studied in deep learning, how you can see each and every grid as a token. Okay, we can apply smaller stride also, grid also, but the thing is it will overlap. If you overlap like by considering 8 plus 8, it takes a lot of patches. Obviously it takes very computationally expensive time. That's the only thing. But you can go with 1616, which the others propose. So like this. Remaining thing is common. This is one patch, this another patch, and so on. Since there is a positional encoding concept, each and every token is like patch is considered as a token, and we have given a unique number to identify this. Unique number. That means why we are using unique number? We are giving it as token, right? How do you represent first is this patch and so on. Okay, that's what positional encoding is in the transformer. Same thing is considered here. Okay, so finally this is the positional encoding value, and we are adding positional encoding with the actual input, and this is a CLS head, which is the representation of entire representation of the input, each patch representation, where this CLS is the actual thing which is used to find the classification task, like it's a dog, cat, or you want to find some object in a medical image, what is the abnormality and so on. This CLS is the actual representation of the entire input. Okay, so yes, see this softmax classifier. So finally, P is the resultant. If it's a classification task, it's a cat or dog. So probability it finds 80% of dog and 20% for cat and so on. Okay, fine. So the main problem with vision transformer, it outperforms your traditional CNN and all the other models what you learned in your basic course. But what is the drawback with this? You need huge amount of data. For example, if you have 10,000 examples, for vision transformer you need 1 lakh examples. That is the drawback of vision transformer. Understand? You need huge amount of data. So what you can do, I have data set here which is huge, then you train with vision transformer, but for specific tasks you have very less amount of data, like transfer learning, where you can use small amount of data to fine tune on top of last few layers using vision transfer. Then that particular small data set can be any application. You can train on a big data set, generalized data set with vision transformer. Then with specific data set, it can be medical data set, image related. So anything you can take, you try to find out, maybe classification, segmentation, whatever you want. Okay. So fine, that is the drawback. So it outperforms ResNet when you have 100 million images. When you have 300 million images, it is better than one. The small amount of data, only 100 million images, then your ResNet is better. You understand? 100 images, ResNet is better. 300 million, since you have huge amount of data, This one is better. Okay. Fine. Now our actual task. So this is almost gone. This is gone. Next 15 minutes at least, I'll show you some research problems where actual research is going on. Now, if you observe, we have seen how to process text related, which is transform or BAT and so on. Now, vision transfer also we have seen, right? Now, I have a different task. Okay. Yeah, this one. So here we are giving this image, and then we are asking. The prompt is what causes this rash. This is the image we are giving, and the prompt also we are giving. What causes this rash? So now, what kind of data we are processing? What is input image, right? What is the problem, right? That means you have to process image and you have to process text also, right? Visual features, textual features. That's what this multimodal learning is. Okay. So some of the models, Flamingo, Vima started in 2022. Now these are different models, video, Llama. Okay. So Gemini. Okay. If time permits, we'll see Gemini 1.5 also. Okay. So first model, very popular model. I'm going to give the high level architecture again. Clip, contrastive learning, image retraining. Okay. Clip is the multimodal learning, the first better model, right? What is this contrastive learning? See this one. It uses the natural language as well as visuals also. Okay, method. So they have created their own data, like with Wikipedia and so on. I'll show you the high level architecture because of time constraint. Yeah, see this one. This is a textual where we have a text encoder and we have a dog, which is again visual features. We have another encoder. Now, the contrastive learning is what is the best match for this text with this image. Okay. So when there is a best match, it try to maximize that loss. Okay. When it is like there's no relevance, then it try to minimize whatever is not matched text with the image. So that's what these are the matched ones in the diagonal. Try to minimize the loss for the other things. I think you might have studied what is the loss function, right? Clip model. So yeah, see this one. It generates text encoder generates textual features in the numerical form. Next, this visual features and then multimodal, which is combining and using cosine similarity to find the score. Okay, so it was very good research paper. If someone is interested, yeah, how we are actually mapping in 2 dimensions. You can see this one, this numerical values, this red one. So, for example, if it is a puppy and you are doing a puppy image, so both are mapped. Okay. Similarly, another image which is relevant, text and image is matching. So both are similar. Try to maximize that. That's similarity. So relevant, try to minimize that. That's the object of what is that contrastive learning is. Okay. So this is one work you can go through and outperform majority of the standard data set. 27 data sets we tested. So like Stanford cause, country 2-1 food. These are all standard data sets. See this one. This is the accuracy they have given outperformed with the existing models. Of course, on few data sets it failed. After this, we come up with again another model called Align and so on. Okay, so, but I am not discussing all those. This is another example of Flamingo. Okay, so what is this? GPT-3 also used partially the idea of this Flamingo model. Okay, what is this? Yes, can you read this? Yeah, this is interesting. We have given an image, and the question is, what do you think the capacities of these are? Something. So, what is this? When you can see this image immediately, say this is a blob, this is artist, and so on, right? But machine need to tell you the answer. You have given a prompt, you have given an image. Now it has to find out. So, how it is possible? Yes, this text and image matching. So you have to train such pair of text and image, vast amount of data, then it can perform some reasoning and it can provide with the available data if you train well, right? The floppy disk is 1.44 MB and the CD is 700 MB and so on. So everything, the question like, what is hard about this? You see this one, the question is, what country is this? Why do you think so? See this one, just identify this flag and it is answering, this is so and so country's flag. Understand? So similarly, some more visual dialogue things are there. Okay, you can see what is this picture. It is a bowl of soup. So you can also reason like if it is answer, like the answer is wrong, you can give something like to correct the model. So the Flamingo model works on this, and even you can see the website which is blurred, even it is able to answer. Okay, so why I am saying all this? This is the design for one specific general application. So why can't you explore it for different applications, right? Suppose, I'll quickly go through architecture. I'll skip because of time constraint. Okay, I thought 1.5 hours. See this one, Gemini model, the recent Gemini model. How many multi-modal inputs it's considering? Text, okay, video, audio, and speech. Different modalities is taking, and there is a what is this in the middle one? Transformer based model, not exactly transform. Okay, I have shown you right clip kind of model. So they updated with whatever the flaws in the earlier models, and they try to update it, and they come up with multimodal data, and it can give us the data image. If you want image to generate, it generates the image, and if you want something else also, it will provide what kind of description you want from that image or video also. So see the beauty of this Flamingo model. So of course this is not open source, it's not available, but at the same time you can explore some equivalent free models are available in Hugging Face. Okay, see this one, a prompt. The prompt is write code and rearrange these subplots. Okay, the question is this one. We have given the prompt and this image also. The Gemini model generated, it has used this as input image, and it has updated according to not exact. I don't want this. I want some modifications to this graph and generate the code. It has generated the code, and the output of that is this one. Slight variation of this. Understand? So what kind of data it is taking? It's taking text, and it is also taking the question. It's generating code. Understand? So it outperforms video understanding. If you see, this guy is playing. This is a video actually. Okay, how could this person improve their technique? So it has gone throughout the video, frame by frame it analyzed, and it is giving the answer. The soccer player needs to work on the ball, striking techniques. Like it is giving the suggestion, it is not striking it properly. So it has to do like this. Just imagine. Okay. Now, can you apply this, for a video, some kind of, for some diagnosis, people they'll self all camera into our body. It will take video, then they'll check what is happening inside, and they'll give doctor or radiologist will suggest you this is the issue, you have to go for a surgery or something else, right? So this is a general. Can we apply it for some other real-time applications? Yes, it is possible. You explore. Okay, so you can take it as a project, people, and you can try. So I'll show you some of the examples. Transformers in medical domain where I'm working. So maybe in 5 minutes I can quickly close. So transformers, see this one, in medical a lot of areas are there. So currently we are working on report generation. Okay, so we have some results and we communicated. So otherwise I would have explained that code initially. Classification, segmentation, reconstruction, and so on. This is just transformer based only. If you combine transformer and vision models, or videos related. You can also try different, like applications. These are different recent research work in this medical image domain on transformer based and hybrid model, which is a transformer, vision transformer, and basic text based one. Okay, lot of work. So I have given reference also. You can go through. Yeah, open research problems. Now in the medical domain, we identify some open research problems like this. I have data scarcity issue in medical domain where because of privacy issue and all, people won't share the data. They'll share 10 images, 100 images. If you see how many images we have trained, actually thousands, billions of images we trained for vision transformer. But actually in real time, you don't have that much patient data available, this size data available, annotated data available. So what do? I need a model with limited data. I could predict what is the disease, what is the problem, what is the issue, right? So that's why you can use a pre-trained network, and then on top of that, with the limited data, you can train. Okay, so the research is going on in this self-supervised learning, semi-supervised learning, and a combination of that. What is semi-supervised learning? I have very few labeled data. That means, a doctor annotated this is a problem, this is not a problem, like that. So I have only 100 examples, such examples, but I have 10,000 examples which are not annotated, that means not labeled. Okay, with the small limited annotated data, how I can classify all these examples? That is self-supervised learning, where there are some models, still people are working in self-supervised learning, where I have semi-supervised learning, where I have limited data of labeled, okay, large amount of data which is not labeled. So still you can achieve with self-supervised learning. This is open research problem. Work is still going on, so people can explore this. And self-supervised learning. So this is the model itself. It's a complex task actually to label a data. So can we give that task to a machine? Yes. Model itself from the unsupervised data, it can assign labels, pseudo labels. We call it as that is called self-supervised learning. If you observe, you can use generative models. And you can use few-shot learning. What I'm saying is few-shot learning with few examples, even zero-shot learning. Some of the model clip work based on zero-shot learning. Of course, there is a failure rate, but because without any training example, if I say yes, this student is so and so, you identify, but I don't give a single image of that person. That is called zero-shot learning. When I say few-shot learning, 5 different views of that images of that particular student I'll give. Now you can predict. That is few-shot learning. So combination of this, lot of research is going on. So generative model, self-supervised learning, semi-supervised learning, few-shot learning. Combination of this. So lot of research is going on. People can explore. Yeah, you can see clip which I explained, which was used for general images, right? Clip, contrast to learning we discussed just now. But that same clip with some little modifications, they use it for medical image, report generation and all. Okay, so yeah, this is a complete view of medical language models, large language models in medicine. Okay, so this is data, old data, some of the benchmark data sets, right? So we are using these kind of pre-trained models available. Whatever I discussed, some of them they updated according to the data sets, and then train, evaluate. Then take the feedback also. You can take the feedback from from the doctor or the patient, and then generate some new data, take this feedback, use reinforcement learning, try to update the data set, try to update the model parameters, and so on. Okay, so these are the metrics actually to say this model is working good or not. Okay, red, blue, and so on. Okay, so it's kind of life cycle. I think is there in the next slide also. I'll close here. Not this. Yeah, see this one. Please generate a medical report based on the image. 2024, 2025 recent work is I give just image. Like a doctor, it has to write a report. Okay, I have given image and a prompt. That's all. It has to generate the report. How it is possible? We have seen that clip model. Clip model, you need plenty of data, analytic data. Okay, so it has provided, of course, model by model, GP, LLama, large language models, one of the model, GPO and MED-PO. Plenty of models are there you can explore. So here this model got 90%. Okay, so combination of image, video, different modalities. That's what multi-modal learning is. Maybe the same concept you can apply for your sensor data, some IoT applications you are using, right? So for a patient emergency case, for example, one real-time application, sensor data, then nearby hospital you need to search where is your location, where is the nearby hospital. So some accident happened. Okay, so ambulance need to you have to give path to the hospital. That is through routing you can get the path. At the same time, parameters what is the issue and all you have to get. So multimodal data you can quickly extract in emergency case, so the doctor will understand at least what happened and what is his condition, so that he can start his treatment. Can you develop such kind of system? Yes, it is possible using multimodal learning. At least simulation you can do. Okay, so yeah, I'm stopping here. Yeah, any questions? Yeah, still I have some open research problems. We have time constraint to stop here. Yes. Any questions? So I have a few works in this multimodal learning, but that is communicated. So they're not yet published. That's why I could not disclose that. Otherwise, I would have at least 5 to 10 minutes to discuss my work. Okay. Yeah. Feeling so hungry? No questions? So for the question, I can that has answered. I'll add few more points to that. Some student asked. So there is a concept called prompt engineering. Okay. So prompt engineering is not so easy. You have to give a correct prompt. How to give correct prompt? There are different steps actually. Okay. If you can give correct prompt, the model will not be biased. Okay. Prompt engineering, advanced prompt engineering is there. Okay. So earlier, I have given one model, asked them to run students practical session completely 3-hour session. How to give you a prompt, how to reason the model and all I have shown. But this is kind of conference where I can explain the recent works, what you can do, what kind of project you can select. That's why I discussed open research problems, some work we are doing, and some recent works, worldwide renowned work I explained. Okay, prompt engineering, how best you can give the prompt, accordingly model will give you the response. The subject is prompt engineering and advanced prompt engineering. Yes. Which one? Yes.
Yes, sir. Sir, so you just have suggested the prompt engineering topic. But these days, every conversational chatbot is being fine-tuned even more. And as you have already explained about bird classification or other items, there the intent is not, context is understood intelligently. So there is also a whole where we see a threat to prompt engineers, as even I am working on prompt engineering, because the models are becoming smarter every day. So in at some point in the future we see that there would be a threat to prompt engineers because the model is intelligent enough to map the intent of the user. So how to deal with this?
Just still research is going on in that prompt engineering, prompt injection. Okay, whether the given prompt is you want to it's a kind of threat really the prompt is, or it is really actual prompt which is required some data or suggestion something. So still the work is going on, active research is going on for your question. Still work is going on. Even I have we just recently applied one project on prompt injection. So 1 crore project for DT, Department of Electronics. Okay, so very active research is going on in this domain. So as of now, it is open research. Yes, whether the given prompt is actual prompt or it is kind of a prompt injection which want to kind of do some kind of malicious things to your order. That is still active research is going on. Okay, it's open research problem. Okay, yeah, good
Yes.
question. Any other questions? So at least did you find at least few project ideas from my talk? Okay, very good. That's all for today. Okay, yeah, thank you.